Hello everybody. Today I would like to speak a little bit about packet forwarding at layer 2 of OSI model. So let's get started. This is our contents of today's presentation. We'll speak a little bit about MAC addresses, we'll speak about collision domains, we'll speak about broadcast domains, broadcast traffic, VLANs, trunks, native VLANs, allowed VLANs, and switch ports and interfaces. Let's speak about MAC address. The data link layer for direct host communication is using addressing beneath the IP protocol stack. Each packet from the network layer receives its header and trailer to form a frame at this layer. And header contains a unique identifier or a media access control MAC address for communication within a network segment for Ethernet protocol. Other layer 2 protocols are using entirely different method for layer 2 addressing. In OSI model, MAC addresses are used in the media access control sublayer of data link layer. And MAC address, so what is MAC address? MAC address consists of 6 group or octets containing 2 hexadecimal digits. First group of octets are called organizationally unique identifier, and these 3 octets are assigned to device manufacturer. And if each manufacturer is responsible for ensuring that the second 3 octets are unique. Each device on the network segment is listening for network traffic that contains its MAC address as destination address in the frame. Only when the device receives a frame with its MAC address as destination, it can decapsulate the frame and move the packet to the layer 3 for processing. The only exception for this rule is broadcast traffic with destination MAC address FFF, 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 FF. So all Fs for broadcast traffic is the exception for this rule. And this broadcast frame has to be processed by all devices in the same network segment. In most cases, broadcasts are not forwarded beyond layer 3 boundaries. Collision domains and hubs. So what is collision domain? Collision domain is a network segment connected by shared medium where simultaneous data transmissions collide with one another. The collision domain applies particularly in wireless networks, but also affected earlier versions of Ethernet. A network collision occurs when more than one device attempts to send a packet on the network segment at the same time. Members of a collision domain may be involved in collisions with one another, and devices outside the collision domain, they don't have collisions with those devices which are inside the collision domain. To avoid packet collisions, network devices use carrier sense multiple access with collision detection mechanism, or CCNA-CD. Using this mechanism, any network device, before gaining access to the network, needs to check if the network is free. If the network is free, then device starts transmission. But if the network is not free, then device needs to wait a random amount of time before trying. Another case, for example, when the network is free, but 2 devices access the line exactly at the same time. In this case, we have collision. Signals collide, and when collision is detected, those devices, they back off and wait a random amount of time before trying. The situation between switches and hubs are different in the network, because hub itself is like collision domain. For example, on this example, we have 2 simple networks interconnected with hub, one network and another one with switch. And when we have hub, all devices, they are sitting in the collision domain. But when we have switch in the network, we have only collision domains on the links between switch and hosts. But for example, we should differentiate between full duplex and half duplex. If we have full duplex, we're not going to have a collision domain. because we use two pairs, one for transmission and one for receiving. That's why we don't have collision domain in full duplex. This is for everything for collision domains. Network switches and broadcast domains. Network switches create virtual channels which enhance scalability and stability of the network. Switches use MAC address tables to associate the host's MAC address to the port, which is the source of traffic. Using this association helps to replace flooding traffic out of all ports with forwarding only to the switch port associated with the MAC address of the destination host. And these MAC address tables, they are located in the content addressable memory on the switch, and they provide two results. One is for true and 0 is for false. If a switch needs to transmit a segment with MAC address that is not in the MAC address table, the switch performs unknown unicast flooding, which is forwarding the segment out of every switch port except the ingress port. Broadcast traffic is intended to be forwarded to every network device on the LAN, and the switch forwards it out of every port. Broadcast traffic diminishes effectiveness of network switches because network devices stop transmitting due to carrier sent multiple access with collision detection mechanism. Broadcast traffic does not cross layer 3 boundaries, and all network devices residing in the same layer 2 segment belong to the same broadcast domain. Let's see how unicast traffic works. For example, we have a small network of 4 hosts interconnected with one switch, and switch already has got all MAC addresses and associated them to the interfaces. If PC1 needs to do transmission to PC3, it just sends to frame with this destination MAC address of host 3, and switch just forward this traffic to interface G03 for PC3. What about broadcast domain? Broadcast traffic, sorry. For example, a host 2 needs to transmit broadcast request. It sends broadcast frame to the switch, and switch forwards this traffic to all its ports. VLANs. A VLAN or virtual LAN is a group of network devices on one or more LANs, which are configured to communicate as if they were connected to the same wire, even though they may be located in different LAN segments. LANs are extremely flexible, as they are based on logical, not physical connectivity. VLANs define broadcast domain in the layer 2 networks. Network devices can only communicate with network devices within the same VLAN using traditional layer 2 or broadcast traffic. VLANs are usually associated with IP subnetworks when all network devices with a particular subnet belongs to the same VLAN. Traffic between VLANs, between different VLANs, must be routed on the router. VLANs address issues such as scalability, security, and network management. Routers between VLANs filter broadcast traffic and can enhance network security, perform address summarization, and mitigate network congestion. To find out which frame belongs to which VLAN, we need to tag them somehow. And for this purpose, we have 802.1q standard, which defines that 32-bit tag should be injected into Ethernet frame after source MAC address field. Here on the picture, we have example of the frame, and we can see that VLAN tag is injected after source MAC address field. VLAN tag itself has 4 fields, and the first field is tag protocol identifier. This is a 16-bit field, and it is set to 8100 to identify the frame as an 802.1q tagged. Second field, this priority code pointer. This is 3-bit field, which refers to the 802.1p class of service as part of layer 2 quality of service between switches. Third field is drop eligible identifier. This is 1-bit field, which indicates that frame can be dropped in the presence of congestion. And the last one is VLAN identifier. This is 12-bit field which specifies the VLAN to which frame belongs. The hexadecimal value 000 and FFF, these values are reserved. And the reserved value 00 means that frame doesn't have VLAN ID. 802.1q tag specifies only PCP and TEI field in this frame, and it is referred as priority tag. The VLAN ID FFF is reserved for implementation means and can't be configured or transmitted. So, and the last note that according to 802.1q standard, if the switch port has access configured as access port, then only untagged frames are to be accepted on this port. Any tagged frames are to be dropped, including the ones matching the VLAN ID. As we discussed on the previous slide, the VLAN identifier has only 12 bits, which means that there can be only 4096 unique VLANs. VLAN 0 and VLAN 4095, these VLANs are reserved for system use only, and VLAN 0 is reserved for 802.1p traffic. VLAN 1, this is default VLAN from the normal range, and it can be used, but it cannot be deleted or modified. VLANs from the 2nd to 1001, these VLANs are in normal range and they can be added, can be deleted, or can be modified. VLAN 1002 to 1005, they are in normal range, but these VLANs are reserved for FDDI and token ring, and these VLANs cannot be deleted. VLANs from 1006 to 4094 are in extended range, and these VLANs can be added, deleted, or modified. Then they can be used. VLAN configuration. The VLAN configuration itself is stored in vlan.file. This file is located in non-volatile memory, and depending on the switch model, it can be either flash memory or NVRAM. Deletion of this file may cause inconsistency in VLAN database, and to check if the file is presented in the file system, use the command dir flash or dir NVRAM depending on the switch model from the privileged exec mode. To create VLAN, use command VLAN and then VLAN ID in the global configuration mode. Each VLAN can be assigned a friendly name through the VLAN submode configuration command name and then VLAN name. If you don't create the name for VLAN, system will give your VLAN default name, which is VLAN and then 4 numeric digits with leading zeros, for example, VLAN 0020. And the name, friendly name for VLAN should be 32 characters. VLAN creation is completed only when the command line interface has been moved to the global configuration mode. So when you type VLAN and VLAN ID and then VLAN name, then when you leave in this VLAN configuration to mode to the global configuration mode, only at this moment system creates VLAN. To delete VLAN, use the no keyword in the front of command VLAN VLAN ID. If VLAN gets deleted, then ports associated with that VLAN become inactive and no traffic flows. If deleted VLAN was a member of trunk port, only that VLAN is shut down on the trunk. Verifying VLAN. Verification of VLANs and assigned ports can be done with the command. It starts with show VLAN, and then we have some optional keywords: brief, ID, VLAN ID, name, and summary. Using only commands show VLAN itself provides output which is split into 4 main sections. First section is VLAN to port assignment, second section system MTU, third section is span session and private VLANs. We will see it a little bit later in the practice. These optional keywords are the following. For example, if you use brief, it will display port to VLAN mappings, short port to VLAN mappings. If you use ID VLAN ID, then system will display display output from a show VLAN command filtered by the specified VLAN ID. If you use name and then VLAN name, system will display output from show VLAN command filtered only by specified VLAN name. So you can use either VLAN ID with ID optional keyword, or you can use VLAN name with a name optional keyword. Summary displays a count of existing VLANs, number of VLANs participating in VTP, and number of VLANs in extended range. Access port. Port on the switch can be configured as an access port and can be assigned to only one VLAN. Access port carries traffic from the specified VLAN to the network device connected to that port, or from connected network device to the other devices in the same VLAN. Frames received or transmitted on the access port are not carrying 802.1q tags. These frames are untagged. If there is no VLAN configured on the port, by default it is assigned to default VLAN, VLAN 1. Access port can be configured manually with the command switch port mode access in the interface configuration mode. VLAN assignment to the port can be done with command switch port access, and then we have two options. We have VLAN with VLAN ID, or we have name with VLAN name. This is new option for this command. Trunk ports. Trunk port is used to carry multiple VLANs on the single link connecting switch and another switch, router, or firewall. Basically, this is like pipe which is carrying multiple frames tagged with different VLANs. When the switch receives the frame on the trunk link, first it examines the header and associates that frame to the proper VLAN. Then the switch removes the 802.1q header and forwards frame to the next port associated with the MAC address for that VLAN. To statically define the trunk port, we need to use command switch port mode trunk on the switch interface. To verify status of the trunk port, show interface trunk command is used, and there are three sections in the output. First section shows ports which are in trunk mode, encapsulation method, status, and native VLAN on the trunk ports. The second section is dedicated to show all the VLANs that are allowed on the trunk port. The third section displays all VLANs that are allowed across the trunk port and are in the spanning tree forwarding state. Native VLANs. According to IEEE 802.1q standard, any traffic that is transferred or received on the trunk port without 802.1q tag is associated with the native VLAN, which is by default VLAN 1. Native VLAN should match on both ends of the trunk link, or traffic can change VLAN unintentionally. And in most cases, the error message span 3 to receive PVID error will show up. And this message means that specified interface has received an STP BPDU that is tagged with a VLAN ID that does not match the VLAN ID on which the BPDU was received. This error message additionally will point out that native VLAN is not consistently configured on the trunk link. To configure a native VLAN on the trunk interface, command switch port trunk native VLAN ID is used. And note that best security practice and Cisco security hardening recommendation is to change default native VLAN from 1 to some different VLAN, better to VLAN that is not used and doesn't have attached hosts to it. Allowed VLANs. By default, a trunk port sends traffic from all VLANs which are allowed on that trunk port. However, there are cases when some VLANs need to be removed from the list of allowed VLANs on the trunk interface, and also VLANs can be added back to the allowed VLANs. To manipulate VLANs traversing the trunk link, the following interface mode command is used. This command is switch port trunk allowed VLANs. And then we can specify, we have actually some options. We can specify just VLANs which we want to be added to trunk link, or we have, for example, option all, which specifies all VLANs to be added to the current VLAN list. We have option none, which specifies that non-VLANs to be added to the current list. And option add and VLAN IDs. This option specifies the VLANs in VLAN ID that to be added to the current VLAN list. Remove option with VLAN IDs specifies that these VLANs to be removed from the current list. And accept VLAN IDs, this option specifies that all VLANs to be added to the current list except these specified VLANs. When making changes to the trunk port, it is best practice to use add and remove keywords, because these keywords are more prescriptive. Mistake to use command switch port trunk allowed VLANs and with VLAN IDs, as it will override current list of VLANs on the trunk interface with specified in this command VLANs. So basically, if we use this command, it will override all previous configured VLANs on this trunk interface with VLANs specified in this command.
MAC address table command. To display MAC address table, the following command is used. This command is show MAC address table. Then we have three options. Address MAC address. This command shows entries only for specified MAC address. Dynamic. This option shows only entries dynamically learned. And then VLAN with VLAN ID shows entries with which matches specified VLAN. Additional keywords for command show MAC address table. Some of them we can mention like agent time, which displays agent time in all VLANs or the specific VLAN count. This option displays number of MAC addresses in table for all VLANs or for specific VLAN. Interface lists MAC addresses on specific interface. And static. This option lists static MAC address entries. Some older technologies like load balancing requires a static MAC address entry in the MAC address table to prevent unknown unicast flooding, and we can use this command for this option for this purpose. MAC address table static MAC address VLAN, then VLAN ID, and then we can use two options drop or interface with interface ID. This command adds a manual entry and can associate it with specific interface or drop upon receipt. Command clear MAC address table dynamic. With these options, it flashes the MAC address table for a switch.
And let's discuss some simple commands to show switch port status. To display all relevant information for the status of all switch ports, the command show interface switch port is used. To filter our output from this command by showing information only for specific port of the switch, we can use command show interface, then we use interface ID and then switch port. This is very simple and very useful. And the last useful command for diagnostic of the ports on the switch is show interface status. This command displays the following fields: port, which is ID of the interface on the switch, name, description of the interface if it is configured, status of the interface connected, not connected, or error disabled, VLAN ID for access port, trunk for trunk links, routed for layer 3 interfaces, duplex displays the duplex on the interface. If prefix A, then duplex is auto-negotiated. Speed displays the speed on the interface. If prefix A, then speed is auto-negotiated. And the last one, type, displays the type of the interface for the port. Thank you very much for your attention. If you like this video, you can subscribe for my channel, and next video will be dedicated for some kind of lab where I discuss and I will